Okay, good morning. I need to do some erasing here. So, yeah, good. Okay, so today we continue with chapter 4. Let me remind you from last time. Can you hear me? Is this? You should. Is this better? Okay, so chapter 4. Second lecture. So let me remind you what we've done yesterday. So the main theorem was the following. Well, the main definition may be n-fold matrix. So we start with a fixed bimatrix. Remember, two blocks, R rows, S rows, and T columns. And then we form the n-fold product. And we get a big matrix. And we are looking on integer programs defined by such matrices. So we showed two things. Well, let me actually give the main result then. So the main theorem was we can solve in polytime linear and nonlinear IPs of the form min or max f of x, such that x is in Z and T, an x equals some b, and bounds. And the proof, so just to remind you, the vector x is now encoded in bricks. And each brick has length t, corresponding to the number of columns of each piece here. And all these vectors, the lower and upper bounds, are in the corresponding dimensions, z and t. B is in a vector of length r plus ns, and so on. And the important thing is this is a variable. This is variable dimension. So n is variable. Polynomial time means in the natural binary size of the lower and upper bounds, the right-hand side, the unary encoding of n. A is fixed and not part of the input, this little bimatrix here. And sometimes we need some encoding of the f also, some bound f hat on the largest maximum absolute value. If f is linear, then this is simply the usual binary side of the linear form. Okay, and the proof, just to remind you, because I think I forgot to mention something important. So step one, we compute the Graver basis of this n-fold product in polynomial time. So this was the main content of the lecture yesterday, how to compute the Graver basis of the n-fold product in time polynomial in n. Okay, you remember this. And then, maybe I forgot to say this, but we used then the algorithm of chapter 3. So the second step, use it, and the results of chapter 3 to solve this problem. So what we have done, not yesterday, the day before yesterday, we showed that if we have the Graver basis of some integer program, we can use it to iteratively improve the solutions, find an initial feasible solution, and solve the problem to optimality. So this is the situation, and just to mention again, remind you, if I take this off and I look on an arbitrary array here, and even a linear objective, this is an arbitrary integer program, so it's NP-hard, so we cannot solve it. So what I want to show today is that this simple-looking sparse matrix is actually very useful. So in this lecture and in the afternoon, we'll see some applications. So now I'm going to describe some applications. And in the late afternoon, we'll see more applications, but also we'll talk about something else, universality. So we are actually going to show that every integer program is an n-fold program for some suitable small bimatrix. But I mean, of course, we're not going to show that P is equal to NP, so there's some delicate thing going on, which we will have to explain. So let me just discuss applications now. Some of the applications, there are many applications. And I'll discuss applications from chapter 4. So first of all, something I'm going to discuss in the afternoon in connection with the universality. Let me just mention this. So high-dimensional tables, these are very important application, multi-way tables, or in general, multiply indexed variables. So these are very natural problems. Whenever your variables come, has natural arrangement in like this. So we have some big array of dimension d, let's say, with many indices. This naturally fits. This can be made to fit naturally into this framework of n-fold integer programs. So we are going to discuss this later this afternoon, and some applications to privacy. In databases. And I mean, this is somehow, this is the beginning, but there's a hope that there's much more work can be done in applying these techniques to this area. And what I want to discuss now mostly is multi-commodity flows. And there are other applications which I'm not going to discuss. Some of them appear in various parts of the monograph. So partitioning, clustering problems, packing problems, cutting stores is a classical type of, and more, and so on. So there are many applications. But in this hour, I want to concentrate on two. So multi-commodity flows, and then discuss some further extension. Actually, I forgot. Yeah, I want to talk about something else. Let's call this 4. Yeah, I also want to talk about something very important, stochastic integer programming. Stochastic integer programming. So this is, again, a very important and useful model. So I want to talk on 2 and 3 today. Oh. Well, start with this. So let's look on multi-commodity flows, and this is something I mentioned in the first talk. If you remember in the introduction, one of the examples, I started with a transportation problem, classical transportation problem, and then we moved to multi-commodity transportation problem, and immediately we've seen the polytope is not integer, and the problem is NP-hard, and so on. So let me talk about, so I'll come to this problem soon, but let me first start with a more general problem, so the so-called transshipment. So that's a very nice problem. Transshipment problem. And if you forget the multi-commodity for a second, transshipment problem is the most general flow problem you can actually think of. So it includes maximum flow, mean cost flow, whatever you want. And the problem is the following. You have a graph now, an arbitrary directed graph. So let me give a simple example. Okay, let me do a simple example. So you have an arbitrary directed graph. So I'm going to follow an example which I have in the notes actually. Let's just look on one triangle. Okay. But think of a very complicated graph. So I want to expand the data here, but think of something of a very complicated network flow. Like this, maybe this, something very complicated. Could be any graph, any directed graph. And the problem is the following. Now, unlike the transportation problem, so the transportation problem, we have a partition of suppliers and consumers. If you remember, suppliers and consumers. This was a transportation problem. And here, every vertex can be both a supplier and a consumer. So every vertex, and there are many commodities now, so I'm going to talk about the multi-commodity thing. So for every vertex, we have a number which we are going to call the demand, D, V. V is the vertex, D is the demand, and K means the commodity. So dVk is the demand of vertex V of commodity K, and K is between 1 and L. We have L types of commodity. So this is the L commodity, L multi-commodity transshipment problem. Okay, so it has a demand, and the demand is the following interpretation. If it's positive, then the positive is 5. Then? The other way around. Okay, this is a matter of decision, of course, but so plus will mean that the guy wants to deliver 5 units. And if it's negative, he wants to consume this amount of units. So in each commodity, of course, in each commodity can be only a supplier or consumer. That doesn't make sense, right? But in different commodities, the same vertex may be a supplier or consumer according to the sign. Yeah?
Why wouldn't you call that supply instead of demand?
Because, well, maybe I have a better name actually here. How did I call it here? Supplies, how did I call it here? Supplies, demand, I don't know, I call it demands. Because I want to keep the supplies and consumptions for the bipartite case, for the transportation problem. Supplies, I mean, you're right, maybe you should find some more natural word which can reflect, which fits nicely both for supply and consumption. It's a better word in English. He's going to send this out. Yeah, negative means he gets them in. So, and then you have equations. So the equations now are going to, so this is of course a very simple graph, but I just want to illustrate this. So you're going to have supply-demand equation, I mean supply-consumption or demand equations. So you're going to sum for each vertex, and I should say what is a transshipment then, of course. We have also lower and upper bound as usual on the edges. Upper bound, so UE is capacity of the edge, E, capacity of E. And so we assume that the flow of each commodity is non-negative, and the sum of the flows of all commodities on an edge should not exceed the capacity, as we've done in the transportation problem. What else do we need here? There's an objective function. I'll come to that. And we have equations now. So for every vertex in the graph, whatever comes in, and for every commodity, so, well, sorry, I should define it. So the variables are going to be, this is going to be the flow of commodity K on edge E. These are the variables. They are integer non-negative variables. And so a transshipment, a multi-commodity transshipment is an assignment of non-negative integer values to these variables here, so that for every vertex, the demand is met. So what is every vertex and every commodity, we have to sum over all edges which leave the vertex. So delta plus, let me say delta plus, I mean those that get into the vertex. So I want delta plus are those that get into the vertex. So delta plus are those that get into the vertex. The total amount of flow of commodity K on edges entering this vertex minus the total flow leaving the vertex should equal the demand of that vertex at this capacity. And we should have, okay. So maybe I should simply give an example. And then we should also have the sum of all commodities does not exceed the capacity of that edge. This is something we had before. And then we have some objective function, and the objective function, is to minimize possibly nonlinear cost, where the cost is sum over all edges in the graph. And for each edge, there's a function of the total flow of that edge, and additional functions of this. That's a pretty complicated expression. So this is the objective function. It's taking too much time. So you see, the point is the following. We allow functions we just take into account for each edge and each commodity. There's maybe some cost associated with this specific flow of this commodity on this edge. And there's this ingredient which is maybe more natural. For each edge, you sum the total flow over the edge, which should not exceed the capacity, and you evaluate some cost function of this. So the standard linear problem, you just have this component multiplied by some cost per unit. So this is the much more general problem, and it's a multi-commodity, so it's a very difficult problem. Yes?
So could you explain the GEK?
So GEK, you have for every edge and every type of commodity, you may also allow in the cost function to have some cost which depends only on the value of the flow on that edge of a specific commodity.
Okay, some kind of surcharge on a particular commodity.
Yeah, maybe certain commodity is more expensive for some reason, so you have to somehow account for that. But anyway, it allows you more flexibility, so you can always take this to be 0 and just be left with the left-hand side. I mean, this you can take this to be identically 0, and then it's not there, and then you still get something more general than the usual linear problem. Let me just give a quick example here, so it's not completely in the air, this model. So let's do an example here. So here is an example. This triangle, very simple. I mean, this is really very simple, but just to illustrate. So suppose I have here demands. In the first commodity is this demand, the second is this demand. So these are the demands at the vertices. -2, 1. And suppose the capacities are unbounded, so UE is infinity, there's no bound on the edges. And suppose the function, there's no G, so the G's are zeros. GEK equals 0 for every E and every K. We have two commodities. So L equals 2. What else? Capacities now is to tell you what the objective function f is. So f of e for every edge, f of e of how many arguments does it have? 1. So f of e of y equals y squared. Or maybe I should write it more explicitly. So f e of x1e plus x2e equals x1e plus x2e squared. And now I'm claiming that the following is a feasible flow transshipment. So let me just explain this, write this down, then we can explain this. Okay. So, yeah. Okay, so let's see. This is the network, this is the graph, directed graph. At each vertex I have a demand in the first commodity, a demand in the second commodity. So this guy here is a supplier of 3 units in the first commodity, and he wants to consume 3 units of the second commodity. So is this clear? And I should decide how much flow on each edge of each commodity to put. So this is some solution here. These are the x. This is x e. And let's see that everything is met. There are no bounds on the upper bound, no capacities. These are non-negative integers, so this is fine. So let's look on this guy here. He sends out 3 units, right, and gets 0 in the first commodity. Are you following this? I mean, look on the first commodity. This guy sends out 3 units and gets 0 units, so it is fine. He sent only 3 units. Look on the second commodity, minus 3. So this guy sends out 0 and gets here 3. So this is fine, again. He gets 3 in. And similarly for the others, maybe this is more interesting, this guy here. Let's see. So he wants minus 1 here. So he gets 3, sends 2, so he's left with 1, which is what he wants to consume, and so on. So this is the model. And so let me show you that this is an n-fold integer programming problem. Okay, so let me, well, it's going a little bit slower than I intended to, but okay, so let x1 so in general, so okay, so let me, not so easy to, so formulation, it's an n-fold program, n-fold IP. So suppose a graph has S vertices, T edges. S vertices, T edges, and well, we have L commodities now, L commodities. And some functions like this. And so we can write the program in the following way. Do I need some more information here? No, that's all I need. This decay. New. Okay, so let me denote by xk. There's going to be the vector of flows of commodity k. So this is a vector in zt. And we're going to have one of those for every commodity. So we have t edges, and for each commodity I have a vector in t dimensions which represents the flow of this commodity on all edges. Okay? Now I'm going to define, so this is going to be for k equals 1 through L. That's probably the most complicated modeling example I'm going to do in these lectures. I already see it's a little bit, takes quite a lot of time. And now, so the capacity constraint, how do they look like? Sigma x k over the commodity is less than or equal to u, where u is again the vector of capacities. Right? But, so again, this is a vector in the edge. All the vectors are now in the edge space. So this is a vector on the edges telling you what the capacity of each edge. And each one of those is a vector telling you how much flow to send on each edge in each commodity. But I want equalities because our standard form has equalities. So I define a slack commodity. So define slack commodity. And let's call it x0, so it's consistent with this notation. This is going to be defined to be u minus this sum of the others. And this is again a vector in zt plus. So this is x0. And now I need one piece of information, and we can actually write down an n-fold integer program for this. So let me continue on this blackboard here. So let's D be the S by T incidence matrix of the graph. So who knows what the incidence matrix of a directed graph is? The incidence matrix of a directed graph, who knows? Can you lift your hands? Yeah, so I see not so many actually people are excited about saying yes here. So let me just illustrate. Suppose this is our graph here. Let's say a simple graph. I don't know. This graph, let's say, and let's give the edges numbers now, and the vertices also. So the vertices gets number 1, 2, 3, 4. Let's say, and the edges, right, v1, v2, v3, v4, and the edges, let's say e1, e2, e3, e4, e5. So the incidence matrix is indexed by vertices on this side, edges in this side. Edges means directed edges. And we have ones and minus ones according to whether the edge enters or so. Enters means pushing flow, so this is a plus. So let's look on E1. So this is V1, V2, V3, V4, E1, E2, E3, E4, E5. So let's look on E1. It takes away flow from V1, so it's minus 1 here, pushes flow here, so 1, 0, 0. E2 takes away flow from V2, so minus 1 here, enters V3, so 1, and so on. So this is the incidence matrix of the directed graph. Every column is exactly 1, minus 1, 1, 1, and the rest are zeros. And now you can easily see that using this gives me exactly these equations. Because somehow you see on each, if I multiply from a vector of edges, I get exactly the equations for vertices. So using this notation, I can write this multi-commodity flow problem in a compact form as follows. So I'm continuing here. So then the transshipment problem becomes is the following. I need actually one more thing here, the demands. So the demands here, let me also write the demands, dk is a vector. The demand for each commodity is a vector in what dimension? Well, who has the demands? Vertices, right? The vertices has demand, so this is now a vector in ZS. So the flows on the flow on each commodity and the capacity are vectors in the edge space, so ZT. And the demands for each commodity are vectors in the vertex space. They can be negative or they can be also negative, as we have seen. And also I need to make things consistent. I need to define a new commodity, a new demand vector for the slack commodity. And this is just the equations are over-determined. So this is simply, you get it simply, it has to be, simply has to be this D matrix times U, the capacity, minus sigma dk k 0 up to L. So this is, just a redundant equation, but we have to do it in a nice way. So this is part of the data, the demands for the commodities 1 through L. U is the capacity is part of the data. The matrix D defines the graph. So it's also part of the data, and then this is determined. And now we can write the equations in the following way. So we are going to minimize the cost function. The cost function is going to look like this. So we sum over all edges. Let me write them like this. E goes from 1 to T. We have T edges. F sub E. So F is the function of the total flow on the edge. But how can I express the total flow now? I have one variable which can allows me to do that. The slack variable. So U minus the slack variable on this edge, this is exactly the flow of the other thing, right? So this is really the flow of the total flow of real commodities on that edge, plus the sum over all commodities of GE, K, XKE. This is the objective function, and time is running short here, really. And then the equations are now such that, well, first of all, X has to be a vector of integer, non-negative integer, and I have now the slack commodity also, so something like that. XL, each XK is a flow on the edges. So the edges, we have T edges, and it should be non-negative. And integer, we have the upper bounds. So I should actually write the upper bounds, maybe. The upper bounds, no upper bounds now, because this is somehow obtained through this. So no upper bound, just no negativity. And the equations, that's the punchline, really. No, we have equation. Okay, and the equations, so the main thing is the equations. The equations, there are two types of equations. First, the capacity now with the slack flow is an equation. What is the equation for the capacity? Well, I sum all the vectors of all of the flows of all commodities, including the slack, and this should be equal to the total capacity. That's one equation. These are vectors in the dimension of in the edge space. And then we have the demand equation. The demand equations are all of this form. D times xk equals dk. K goes from 0 up to L. Okay, we are close to the punchline. It's a little bit technical, perhaps, but I want to do this modeling once and for all. Okay, so this is our integer program. Now, do you see why this is an n-fold program? Well, so we claim this is an n-fold program. And what is the bimatrix here? So the claim is, so suppose actually, let me assume, suppose that each FE and GKE is convex, and this makes sense, convex univariate. So it looks something like this. And I mentioned this earlier in the introduction. This accounts for congestion. If you have more traffic, more flow on an edge, the cost should increase non-linearly. So this makes sense. Now, if these are convex, then know that this is also convex, each one of those, and this is also convex. This remains convex. And so what is the expression here? It's a separable convex function, right? So let's call this function h. So then the IP is, we want to minimize a separable convex function of all variables such that the total vector here lies in Z L plus 1 T. So edges time commodities plus the slack commodity. X is non-negative. And the L plus 1 fold product times X equals B, where B is the following vector: U, D0, D1, DL, and A is the bimatrix D and IT. Now this completes the modeling here. Took much longer than what I really intended to, but so again, the punchline is the following. Take your graph. Take the incidence matrix of the graph, D, put on top of it the identity of the number of edges. You get a bimatrix now. Form the L plus 1 fold product of that. Form a vector B where the first piece is the capacity vector, and this gives you this equation. You see the sum here corresponds to the equation coming from the first part of the n-fold product. So the n-fold product is now like this: IT, 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 D, D, and D. This is the fold product. So the top part gives you this equation, the capacity equation, and the bottom part, for each flow of each commodity, you get a separate demand equation like this. And so you get it in this way. So this is an n-fold program, and you can solve it in polynomial time for a separable convex function. Now, what's the problem with this? Of course, this is a very hard problem. Even two commodity transshipment is immediately NP hard. So let me just explain this and see what the conclusions are. So if you lost the model, I mean, if you got lost a little bit on the modeling, it's not so important. I just want to explain what's the consequence for this problem. So here is a note. Even the linear feasibility, the linear two-commodity transshipment problem over the directed bipartite graph KMN is NP hard. Or actually, let me do it a different way. The L commodity on the K3M bipartite graph is NP hard. That's actually what I want to do here. So suppose you have a variable number of commodities. Suppose you have L commodities, and your graph is a very simple graph. 3 vertices here, and n vertices here. And the directions are like this. Then already for this simple graph, where you have 3 vertices on one side, if you have many commodities, this is NP hard. So we cannot hope for much here. But the conclusion here is the consequence of what I explained here is that for every fixed directed graph G, we can solve the many commodity transshipment in polynomial time for variable number of commodities. So this is something a little bit strange. You see what the graph is fixed now. That's something which is a little bit unusual. So the directed graph is fixed once and for all. It can be very large, 100 vertices, let's say. But we have to fix it, because then the matrix D becomes fixed, and this bimatrix becomes fixed. Or we can let it go, but slowly. So we can also get some sub-exponential something. But the number of commodities L is now variable. And again, usually even the two-commodity flow problem is NP-hard. So here we can allow the number of commodities to be variable. For fixed graph, we can solve it in polynomial time. I don't know if there are natural applications for this. This would be interesting. But let me move to the corresponding transportation problem. And there we have a different consequence. I'm not going to do the modeling. The modeling is a little bit similar to this, maybe a little bit more complicated. But the consequence for the multi-commodity transportation problem is perhaps more natural. Again, this should be a useful problem, but I don't know if natural application, it would be interesting to see. But it's an interesting problem. So for the corresponding multi-commodity transportation, so what is the multi-commodity transportation problem? Now we have a bipartite graph, and we have S1K, SMK, and we have consumptions CKN, and it's a bipartite network. So M suppliers, N consumers, and L commodities. Stochastic integer programming, I think we'll have to wait. Maybe I can say something about this. So this is a special case of this problem, in a sense, right? Because I'm looking on a specific graph now. But now I'm thinking about these as suppliers. So these have only positive demands, if you want. These have negative demands, so these are consumers. And if you model this problem in a little different way, it's more complicated. You get as a corollary, again, for an n-fold program. This is, again, a different n-fold program. This is, again, an n-fold IP. And we have corollary for every fixed L commodities and fixed M suppliers can solve in polynomial time for variable N consumers. So this is a more general, a more natural application. You have, whenever you fix the number of suppliers, so suppose of some, you have some, either in communication, network communication, you have some servers. So you may have, I don't know, 20 servers, and many station access data from these servers. So N is large. or think of some merchandise. So you have some retailer, we have some warehouses, maybe 20 warehouses in some region, and you have many, many shops that take merchandise from that. So it's very natural in operations research applications to have a small, relatively small number of suppliers, servers, warehouses, and a large number of consumers. And so if you fix M, 10, 20, and you fix the number of commodities, again, any, 4, 5, then as n varies, you can still solve it in polynomial time. So this is, and the nonlinear problem also, the congestion-driven objective function. So this is interesting. I should say actually, even for that's something to think about. Even for L equals 2 and M equals 3, the only algorithm that seems to be available, we are aware of, uses this theory. So even if in a very small problem, just 3 suppliers, bipartite graph 3 by n, and 2 commodities, the only polynomial time algorithm that we are aware of is using this entire theory of Graver bases. And maybe there is a simpler way to do it. So this would be a nice problem for someone who is interested in graph algorithms, maybe to find some ad hoc algorithm of better complexity, actually, because the complexity for this specific L2 M equals C is 9, so n to the 9. If I increase the number, let's say, the number of suppliers to 4, with 2 commodities, the complexity is going to be at least n to the 27, maybe more. There's a fixed constant, which is at least 27. So this leads me to some, so let's leave a little bit the modeling for a second. Let me talk about graph, a new graph invariant, which is very interesting, which has to do with this. So let me tell you what is the Graver complexity of a graph. Graver complexity of a graph, or a directed graph. Well, can you guess? I mean, look here on this blackboard. So we have a bimatrix here. Bimatrix. Yeah, the pole again, no fish. Maybe there's some fish behind for lunch. I don't know. We get something more interesting for lunch today. So what did I say? So we have this bimatrix. And now, if you remember from yesterday, we had the definition of a Graver complexity of a bimatrix. The largest type of any element in the Graver basis of any n-fold product. And so now it's very natural, if you have the incidence matrix of some directed graph or graph, you simply define the Graver complexity of a graph or the directed graph G is going to be defined to be the Graver complexity of this bimatrix. The Graver complexity of the bimatrix, where the second block is the incidence matrix of the graph, and the first block is the identity of order, which is the number of edges of this directed graph. And so we know very little on this. This is a very hard problem. So this invariant is very difficult and interesting. And almost nothing is known on this. So let me just tell you that for the bipartite graph K33, so this means we are computing the Graver basis, the Graver complexity of the bimatrix. Well, let me not write it, it's too large. So the graver complexity of the bipartite graph K33 is 9. And that of K34 is at least 27. But we actually don't know the answer here. So here is a very simple graph. 3 vertices on one side, 1, 2, 3, 4, and so on all the edges. And G of K34 is not known. A graph on 7 vertices. So there are not so many examples of graph invariants which you don't know for such small graphs. The only other example, just a second, the only other example which is not, I mean, this example is more complicated, but still there's this something you may have heard of, the Shannon capacity, has to do with coding, capacity of C7, the cycle on 7 vertices is also unknown. 1, 2, 3, 4, 5, 6, 7. So there's another invariant, more complicated. It's also defined actually in terms of certain products. So that's kind of interesting. But this number is actually not going to be integer or rational in general. It may be irrational. So this is a harder invariant. It's also not known for a 7-vertex graph, the cycle on 7 vertices. Yeah, you had a question?
Is there at least an intuitive idea of what this thing should measure?
Yeah, actually, what you mean this one? Yeah, good question. I'm glad you asked it. So I don't know exactly what it measures. I mean, but the importance is that this controls the computational complexity of solving these problems. So this is something I actually wanted to say. So this is a very good question. So the graver complexity of a directed graph controls the computational complexity of solving, let's say, the multi-commodity transshipment problem over G. Transshipment problem over G. So roughly we get a component which is something like this. N to the, not n, well, let's say L. L is the number of commodities. So L to the G of G. So if we have L commodities, you see this integer program up there is an L or L plus 1 fold program. And the complexity of, say, computing the graver basis of this L fold product of this matrix is L to the power of the graver complexity of the directed graph. So this is why this is interesting and important also for algorithmic reasons. Okay, I have 2 minutes, so maybe I should say a word on the stochastic integer programming problem. Okay. It will take a lot of time, actually. What?
You said you were going to say one word about it.
One word. One word, yeah. So let's see if we can say something reasonable in 5 minutes. Well, there's a whole section in the book on this. Roughly speaking, okay, let me just say, roughly, so you can see the detail in it. This is a very useful model. And the idea is the following. You're solving some integer program. And there are 2 stages. So this is somehow a model which is more close to maybe some real applications. You have 2 stages in your decisions. First of all, you have to make some decisions. And let's say you can think about allocating some resources once and for all or something like that. Once you've done that, Then there's some stochastic environment and some probability space there. And with some probability, something comes out. There's some realization of some random variables. And after these random variables materialize, then you have to make second stage decision. So the second stage decisions are sort of in real time. You watch what's happening, and then you make these other decisions. And the objective is to somehow minimize the total cost of the first decision, the first stage decision variables, plus the expected value of the cost of the second stage decision variable, because the cost of the second stage decisions is stochastic. And so eventually you have to make a decision on the first stage, really, so as to minimize this total complicated cost, which involves some expectations. So this is a complicated model. And the way you usually deal with it, you discretize the probability space, and you assume that you have n possible outcomes, n scenarios with some probabilities. And therefore, you get some copies, n copies of the second stage variables. So there's an n lying there, and this n is usually large, because this is the larger n is, the better approximation of the real probability space you get. And so if you write this down, you get something which looks like an n-fold integer program, but unfortunately it is not really. So let me just say one thing about this. So let's forget about the modeling. Let me tell you just what it means about the theory. So stochastic integer programming, we get a transposed NP, transposed n-fold IP. So something like, again, minimizing some objective function that is non-negative, and let's call it y. Y and r plus s, and then y comes from this side, equals some b, and y is satisfies some lower and upper bounds. So again, if you work out the modeling carefully, and you discretize the space to n scenarios, you're going to get something like this. A is again an Rs by T by matrix. And you get something like this. So you minimize some objective function, integer variables, lower and upper bounds, equations. But now the equation, you see, you get this n-fold product matrix, but the vector multiplies it from the left. So to apply our techniques, we need the graver basis of the transpose of this matrix. Yeah, I just need 2 more minutes and then. So we need the graver basis of the transpose of this matrix. Now, the graver basis of the n-fold product we've seen last time. We can do it in polynomial time. How about this guy? Well, actually, let me write, this looks like this. This looks like A1, 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 and then A2, A2, A2. This is the transpose. So what do you think? Can we compute this in polynomial time? Well, let me give you some hint. Wait just a second. What?
Yeah, the only thing we added was taking a transpose.
Yes.
Well, taking the transpose is a very, very simple operation. So.
It depends for what. So for example, if you have a symmetric matrix, then it's a very simple operation. You do nothing. So this is this is exactly why I want to emphasize this, because it looks like a very simple operation, and so what can you say? I mean, maybe we transpose the Gregor basis or something. What do you say? Yeah, thanks. Yeah, that's true. Yeah. Thanks. Yeah, I mean, you can start call him. I simply prefer to call him like this, so it fits into what I want to explain here. But indeed, I got it right, right? Like this, and then, yes, it's a transpose of one of those, right? Yes. So, so it looks like a simple.
Even if it's not symmetric, the biggest issue will just be storing the actual.
Well.
You have to multiply from other sides.
So that's something.
You're saying you cannot do anyhow this from the greater basis?
No, from this one it's not. There's no direct connection.
It's harder.
So yeah, so it's maybe harder. I mean, it's a hard problem, but let me give you a hint. We can solve it in polynomial time, but just for linear objectives. So here's one confusing hint. We can solve it in polynomial time only for the timing, only for linear things. So this is more restricted than n-fold, only for linear. We can solve it in polynomial time. And so, so what's going on here? I mean, what do you think about the Gregor basis? Can you do it, or I mean, in view of this hint, for example, you can solve it in polynomial time, but only for linear objective time, not for separable convex, for example. What? So what are you saying? That? Of A2, yeah, but that's, yeah, good point. Yeah, that's a very good point. So that's exactly, so you're getting into what's an obstacle, really. So it's true. We started there, in this structure, you could somehow look on bricks which were in the Gregor basis of the smaller matrix. And here you have this constraint on each row, you have two matrices. This causes a problem. On the other hand, once you fix, if you make these first decision variables, then the other one separates into separate problem. So it becomes easier. So basically, you kind of touch the main things here. The punchline is the following. The Gregor basis of this matrix, the transpose one, can have exponential size easily. And there's a simple example in my monograph. It's a very simple case. We have an exponentially in n many elements in a Gregor basis. You cannot compute it. You cannot even write it down. But you can somehow bypass this using some of these ideas and some others. And there's so there's another stabilization phenomena going on, and one can exploit this and do something, even though the Gregor basis cannot be written explicitly. And that's something that still needs some more understanding. I should say that there's an extension, actually, for this case, which combines the two for something like this. A3, A3, A4, A4, A4. So suppose you look on some more general setup where you have four blocks, and this one stays here. This one is copied like in an n-fold program in a diagonal, and also here. So it's a common generalization of n-fold and transpose n-fold. So again, for this, the problem can be, the linear problem can be solved in polynomial time, and this is a nice paper by actually Matthias, our Matthias, and I put the umlaut. I always put an e after that, so that's redundant. And Raymond Hemeke and Robert Weissmantel. So there's a nice further extension to this combined situation, but again, only the linear problem, and there's lots of issues here to study further on. I mean, can we solve such problems, or even the stochastic problems with nonlinear objective functions, minimize convex function, and so on? And can we extend these structures further and still get this polynomial time solvability? This is completely open. So let me stop here. So in the afternoon, I'm going to talk about universality and tables. So I hope, I mean, the modeling was a little bit, I think, technical, but. Okay, so have a nice lunch. Seafood lunch with the fish for